Ancient civilizations raised giants of stone using nothing but their bare hands and primitive tools. These colossi stand as some of history's most baffling engineering puzzles. By the end of this journey, you will understand the lost techniques that allowed humans to move mountains of rock. How did workers transport multi-ton statues across miles of rugged terrain? What secrets of leverage and balance did they master to erect these monuments? This is the story of ambition that defied physical limits. What does it truly take to lift a giant from the earth? These stone giants are more than just oversized statues. A true colossus is a declaration carved in rock, meant to inspire awe and communicate power across generations. Think of the Colossus of Rhodes, a bronze titan straddling a harbor entrance, or the stoic Moai of Easter Island, their immense stone faces gazing inland over their people. Across continents and cultures, these monuments share a common purpose. They were often depictions of gods, deified rulers, or mythical figures, their exaggerated scale a deliberate attempt to bridge the gap between the human and the divine. Their immense size was not an accident of ambition, it was the entire point. To stand before one was to feel small, to understand your place in a grander order controlled by gods or kings. This is why they were often placed at the thresholds of cities, temples, or sacred lands, acting as eternal guardians and undeniable symbols of a civilization's unity and technological capability. Creating such a behemoth was a societal project of staggering proportions. It demanded the labor of hundreds, if not thousands, of skilled workers, from quarrymen and sculptors to engineers and organizers. The very act of building a colossus was a powerful political statement, a demonstration that a society could marshal its resources and people toward a single, breathtaking goal. So, what defines a statue as a colossus? It goes beyond mere physical dimensions, though they are always monumental, often standing many times taller than a human. It is the fusion of immense scale with profound cultural meaning. They are physical manifestations of belief, power, and identity. By understanding what these structures represented, we can begin to grasp the sheer magnitude of the challenge their builders willingly faced. This ambition did not emerge from a vacuum. It was born from specific historical conditions, a unique convergence of belief, politics, and emerging engineering knowledge that made the impossible seem necessary. These stone giants were born from moments of peak human confidence. In the fertile crescent of the Nile, under the blazing sun of a unified Egypt, pharaohs sought to cement their divine legacy for eternity. The Great Sphinx of Giza, with its lion's body and royal head, was not merely a statue. It was a statement of absolute power, carved directly from the bedrock during the Old Kingdom, a time of immense wealth and centralized control. Far across the world, on a remote volcanic island, the Rapa Nui people undertook a similarly staggering project. Between 1250 and 1500 CE, they carved the Moai, their ancestors deified in stone, as part of a complex ancestral worship that bound their society together. What drove these cultures, separated by vast oceans and millennia, to pursue such similar and Herculean tasks? The answer lies in a powerful trifecta of motivations. First, religious devotion. A colossus was a permanent prayer, a bridge to the gods meant to secure favor for the entire community. Second, political propaganda. For a pharaoh or a chieftain, a giant likeness was the ultimate campaign poster, an undeniable symbol of their authority meant to awe subjects and intimidate rivals. And third, communal identity. The very act of building something so immense required the coordinated effort of an entire society. This labor was not slavery in the sense we often imagine, but often a form of civic duty or religious service, a shared project that reinforced social bonds and collective purpose. They prioritized these monuments not in spite of their technological limitations, but because of what the construction process itself achieved. It forged unity and demonstrated a mastery over their environment that was both practical and profoundly spiritual. This shared ambition, however, would be shaped by the very ground beneath their feet. The specific stone they chose to carve would dictate every challenge and every ingenious solution that followed. The stone itself was the first great challenge and the first act of genius. Deep within the quarries of Moai on Easter Island, the air was thick with volcanic dust. Here, the Rapa Nui carved their moai from a unique rock called tuff, a compressed volcanic ash that is surprisingly soft when first extracted from the earth. This relative softness allowed artisans to etch the statue's profound, angular features with stone hand picks, but it came with a hidden danger. As the tuff dried and hardened in the open air, it became brittle. A single misstep during extraction or transport could shatter a giant that had taken a generation to carve. This intimate understanding of their material was not unique to the islanders. Far away in Egypt, builders faced the opposite problem with granite. Quarried at Aswan, granite is phenomenally hard and durable, resisting the desert winds that would have sandblasted softer stones into oblivion. Yet carving it required a different kind of brilliance. Workers used balls of dolerite, an even harder stone, to pound channels around the desired block, slowly freeing it from the bedrock through sheer, relentless percussive force. This was not brute ignorance, it was a sophisticated application of material science. They knew that limestone, while easier to shape with copper chisels, was porous and required protective plaster and paint. They selected sandstone for its layered workability and basalt for its tough, enduring nature. The choice of stone was a calculated decision, a balance between the workability needed for creation and the durability demanded for eternity. Every colossus is in part a fossilized memory of the very bedrock from which it was born, but knowing the rock was only the beginning, the true test was coaxing these sleeping giants from their earthen beds. The air in the quarries was a symphony of controlled chaos, a rhythmic percussion of stone against stone. Teams of workers, armed with little more than stone hammers and copper chisels, faced the monumental task of convincing a mountain to release a giant. This was not a process of brute force, but one of intimate understanding and meticulous patience. The first step was always to read the stone, to identify the natural veins and fissures in the bedrock that could be exploited. Once a suitable block was marked, the real work began. Laborers would drill a series of holes in a straight line, a process that could take weeks for a single obelisk. Into these channels they would drive dry wooden wedges. Then water was poured. As the wood absorbed the moisture, it swelled with immense, inexorable pressure, creating a clean fracture along the predetermined line and slowly, miraculously, separating the block from the living rock. One wrong move, one misplaced wedge, and the entire slab could shatter, wasting years of labor. The risks of this delicate operation are frozen in time at the Aswan Quarry in Egypt, home to the Unfinished Obelisk. This magnificent but fractured giant, still attached to the bedrock, is a poignant time capsule. Its cracked form reveals the sheer ambition of the project, while the tool marks surrounding it are a direct message from the ancient artisans, showing us exactly how they worked. In some quarries, when the stone was particularly stubborn, workers would use fire setting, building controlled fires against the rock face, and then dousing it with water. The thermal shock would create a network of small cracks, weakening the stone and making it easier to break away with tools. Through it all, overseers coordinated the efforts, directing shifts of laborers who toiled under the harsh sun. The result was not a finished sculpture, but a rough-hewn form, a slumbering giant that had been coaxed from its earthen bed. This raw block was the canvas, and the next stage would require a different kind of artistry entirely, transforming this unshaped mass into a figure of awe and reverence. The transformation from raw block to recognizable form was a dance of precision and patience. Once a giant was freed from the quarry, artisans faced the monumental task of carving its identity. They began not with hammers and chisels, but with string and pigment, snapping lines and painting guidelines directly onto the stone to map out the statue's proportions. This initial sketch was crucial, a blueprint that would guide every subsequent strike. Then the gradual removal began. Workers used heavier stone tools to knock away large, unwanted sections, slowly revealing the rough silhouette of a head, a torso, or an outstretched arm. This was a dangerous phase. One miscalculated blow could fracture a delicate feature or ruin the entire piece. As the form emerged, the tools became more refined. For the stoic Moai of Easter Island, master carvers wielded basalt adzes, their tough, sharp edges perfect for shaping the relatively soft volcanic tuff into those iconic, angular faces and elongated noses. In the sun-baked workshops of Egypt, craftsmen switched to copper chisels and wooden mallets for the finer work, patiently etching the serene smile of a pharaoh or the intricate patterns of a royal headdress into unforgiving granite. This work required more than just strong arms. It demanded a deep understanding of human and divine anatomy, a knowledge of how muscle lies beneath skin and how to convey power and benevolence in a curve of stone. These skills were not learned from a book. They were passed down through generations from master to apprentice in a continuous chain of tradition that turned rock into reverence. The final touch was the smoothing. Artisans would rub the surface with abrasives like sand, using water or oil to create a slurry that polished the stone to a fine finish. This process erased the tool marks, giving the Colossus a seamless, almost supernatural skin. Yet sometimes the marks remain. Look at the Colossi of Memnon, two massive seated figures in Egypt. Centuries of wind and water have worn away the outer surface, but in the protected crevices, you can still see the precise chisel strokes of the ancient workers. These faint grooves are like fingerprints, a direct connection to the individuals who stood where we stand now, their hands shaping eternity. This entire sculpting phase was a testament to the human spirit, a fusion of artistic vision and painstaking craft. But a completed giant, no matter how magnificent, was still a prisoner of its birthplace. The true engineering marvel, the logistical nightmare, was about to begin. How do you move a mountain with the giant carved and polished? The true test of will began, moving a mountain of rock across miles of unforgiving land. This was an operation of staggering coordination. Visualize hundreds of workers, their muscles straining, pulling on thick ropes wound around a massive stone sledge. The ground itself was their first enemy. To overcome it, engineers constructed temporary roads of compacted earth or laid down tracks of wooden logs, creating a semi-stable surface for the colossal load. The physics were both simple and brilliant. By placing the statue on a sledge and dragging it over these log rails, workers effectively turned sliding friction into the far lesser rolling friction. They became masters of lubrication, pouring water or a slurry of mud ahead of the sledge to create a slick, slippery path that reduced resistance even further. Egyptian tomb paintings capture this exact scene, showing teams of laborers moving a giant statue of a noble, a vivid snapshot of a technique used for millennia. Coordination was everything. With a statue weighing dozens of tons, a single misstep could mean disaster. Teams worked in unison, guided by rhythmic chants or drumbeats that synchronized their pulls, maintaining a slow, steady momentum. The greatest challenge often came not from the straight pull, but from navigating obstacles and changing direction. Here, levers became their most vital tool. Workers would insert wooden poles beneath the sledge, using smaller logs as pivot points. Then, with coordinated effort, they would pry one side of the sledge forward, inch by laborious inch, steering the behemoth around a corner or over an uneven patch of ground. This was engineering on a human scale, a dance of leverage and collective strength. Perhaps the most astonishing method of land transport comes from Easter Island, where oral tradition speaks of the Moi being made to walk. Recent experiments have shown this was likely not a metaphor. By using ropes to rock a statue from side to side and pivot it forward with each tilt, small teams could indeed make a multi-ton Moi appear to sway and shuffle its way across the landscape. This walking method, while effective, would have been incredibly risky, a constant balance on the knife's edge between motion and catastrophic collapse. Every one of these methods underscores the same truth. Moving a colossus was a grueling, communal act that pushed the limits of human endurance and ingenuity. Yet for the very heaviest loads, even the most sophisticated land routes were not enough. The true masters of moving mountains looked not to the roads but to the rivers. For the heaviest stone giants, the river became a liquid highway. Water transport was the ultimate ancient engineering hack, turning an impossible land drag into a manageable aquatic journey. Buoyancy did most of the heavy lifting, literally. A statue that would have required the straining effort of 1,000 men to pull over land could be floated on a suitably large barge with a fraction of the force. Ancient engineers built these vessels from whatever their environment provided. Along the Nile, they lashed together papyrus reeds into massive, buoyant rafts, while other cultures constructed sturdy wooden barges, often reinforcing the hulls with extra crossbeams to handle the staggering, concentrated weight. Tomb paintings from Egypt show these very scenes, with a colossal obelisk lying lengthwise on a specially designed boat, being towed by a fleet of smaller vessels, its journey powered by the current and the coordinated paddling of dozens of rowers. This method, however, was not without its own perils. Loading the statue onto the barge was a moment of extreme tension. Workers might dig a canal right up to the statue, float the barge in, and then use a system of levers and counterweights to carefully tilt the giant onto its aquatic cradle. Once afloat, the greatest fear was a capsize. A sudden squall or an unbalanced load could send the entire precious cargo to the bottom of the river, lost forever. To counter this, engineers used counterweights, strategically placing heavy stones on the opposite side of the barge to keep it stable, a delicate dance of balance played out on a grand scale. This entire operation demanded a deep, localized knowledge of hydrology. The builders knew the river's moods, its seasonal floods, and its hidden sandbars. They planned these transports for the time of year when the water was high and the currents were predictable, ensuring a safe passage for their stone god. Perhaps the most spectacular, though largely speculative, use of water transport involves the Colossus of Rhodes. Historians theorize that the bronze giant was not cast in one piece at its harbor-side location. Instead, its sections were likely assembled nearby and then raised into position using an ingenious system of floating cranes and earth ramps, leveraging the harbor itself as a tool. This aquatic ingenuity reveals a profound truth. These civilizations did not fight their environments. They collaborated with them, using water, wind, and wood to achieve the seemingly impossible. But a journey's end brought the final and most precarious challenge of all, standing the giant up. The final, most heart-stopping act was about to begin, standing the giant up. After its long journey, the Colossus now lay on its back beside a prepared foundation, a slumbering titan that had to be awakened. This was the ultimate test of physics and nerve. One wrong calculation, one frayed rope, and the work of a generation could shatter on the stones below. To achieve this, ancient engineers became masters of the gradual tilt. They often built massive earthen ramps against the foundation, creating a sloping path of packed earth and rubble. The statue, still on its sledge, would be painstakingly dragged up this incline until its base hovered just over the edge of its final resting place. Then the delicate dance of leverage began. Teams would insert long wooden levers beneath the giant's back. With rhythmic, coordinated pushes, they would lift it inch by terrifying inch, while other crews simultaneously pulled from the front with ropes, slowly coaxing the multi-ton mass into a standing position. The principle of center of gravity was everything. The engineers had to know the exact point at which the statue's own weight would begin to work for them, tipping it forward into its upright stance. To control this descent and prevent a catastrophic slam, they used complex systems of ropes anchored to heavy stakes or frame structures, acting as braking systems. These ropes were manned by teams who would slowly release their grip, lowering the giant with a control that had to be perfect. We see a variation of this genius in Egypt for raising obelisks. Workers would dig a large, V-shaped pit lined with stone at the foot of a ramp. The obelisk was slid down the ramp, its base pivoting into the precise notch at the bottom of the pit. Then the pit was slowly filled with sand. As the sand was drained from small openings at the base, the obelisk would sink downward, its top rising upward in a graceful, controlled arc until it stood perfectly vertical. This method transformed an act of lifting into one of controlled lowering, a brilliant inversion of the problem. On Easter Island, the process culminated in placing the Moi upon their stone platforms, the Ahu. Oral histories and modern experiments suggest the islanders used a technique of levering and rocking the statue up a ramp of stones, gradually building the platform underneath it as it rose. The re-erection of a Moi in the 1990s using only these hypothesized ancient methods proved it was possible, but it also revealed the immense risk. The modern team reported the palpable tension, the sound of creaking ropes and grinding stone, a feeling that at any moment their work could end in disaster. This final act of raising a colossus was more than engineering. It was a ritual often accompanied by ceremonies and offerings to the gods, a plea for their favor in these last precarious moments. When the giant finally stood, its shadow falling across the people for the first time, it represented a triumph of collective will. It was the moment a society proved it could not only move a mountain, but command it to stand at attention. This entire monumental endeavor, from quarry to foundation, rested on a surprisingly simple yet profoundly effective toolkit. The true power behind these stone giants was not found in complex machinery, but in the elegant simplicity of the toolkit. A master engineer's workshop was a collection of stone hammers, copper chisels, and wooden levers, each one shaped from the very world around them and perfected for a singular, vital task. These were not crude instruments of brute force. They were extensions of human ingenuity, designed with a deep understanding of material and physics. The Egyptians, facing the immense hardness of granite, would never have reached for a soft copper chisel to break a primary block. Instead, they employed balls of dolerite, a stone even harder than granite, using a pounding motion to fracture the bedrock through sheer, repeated impact. On the other side of the world, Polynesian carvers on Easter Island shaped basalt, a tough, dense volcanic rock, into finely tuned adzes. The sharp, durable edge of a basalt adze was perfect for shaving and shaping the softer volcanic tuff of the Moai, allowing for the creation of those sharp, angular jawlines and deep-set eyes. The evolution of these tools tells a story of its own. The development of copper smelting did not just give artisans a new material, it gave them a reusable one. A copper chisel could be reheated, resharpened, and reforged countless times, a significant leap from a stone tool that was simply discarded once it dulled. This advancement in metallurgy, coupled with sophisticated woodworking that produced strong, flexible levers and robust sledges, allowed for a new level of precision and control. Every tool required constant care. Blades were sharpened on abrasive sandstone blocks, and wooden handles were inspected for hairline fractures that could spell disaster under the immense strain of lifting a multi-ton block. This maintenance was not a separate chore. It was an integral part of the daily ritual, as vital as the carving itself. The creation and upkeep of these tools points to a highly organized social structure. There were specialists in every community, the flint knappers who shaped stone hammers, the metalworkers who cast and sharpened copper chisels, and the woodworkers who selected the perfect tree for a critical lever. These artisans were the unsung heroes of the entire operation, their skills enabling the grand visions of the rulers and priests. We can still see their work today, not in the tools themselves, which have often rotted or rusted away, but in the marks they left behind. On the unfinished obelisk in Aswan, the precise, repetitive pitting from dolerite pounders is clearly visible. On the Moai, the parallel grooves from basalt adzes tell us exactly how the carvers moved their tools across the stone. These marks are a frozen record of labor, showing us that different workers had different specialties, some roughing out the form, others refining the features, and a final team dedicated to the polishing. This entire sophisticated system of instrumentation underscores a profound truth. The resourcefulness was not in having magical tools, but in maximizing the potential of the ordinary. Yet these ingenious implements were nothing without the strength, skill, and spirit of the people who wielded them. This human machinery was the true engine behind every stone giant. Behind the symphony of chisels and the straining of ropes stood a highly organized society, a civilization marshaled for a single, breathtaking purpose. Think of the sheer numbers involved. Raising a single colossus could require the coordinated effort of hundreds, sometimes thousands, of individuals. This was not a disorganized mob. It was a meticulously structured workforce, operating under a clear hierarchy of overseers, foremen, and skilled specialists. In ancient Egypt, this system was so refined it resembles modern project management. Papyrus records and tomb inscriptions describe a world where labor was divided with precision. Quarrymen, the strongest and most resilient, worked at the source, freeing the stone from the earth. Then, the master carvers took over, their years of training allowing them to transform a rough block into a divine likeness. Finally, the transporters, a small army of rope pullers and lever operators, moved the finished monument. Overseeing it all were the scribes, the ancient equivalent of data managers, who meticulously recorded daily progress, material usage, and rations distributed, ensuring every aspect of the project was tracked and accountable. This massive manpower was often supplied through a system of conscripted labor. In Egypt, it was known as the corvée, a form of national service where citizens were drafted for a period of time to work on state projects. These were not slaves in chains, but farmers, fishermen, and craftsmen fulfilling a civic and religious duty. In return, the state provided them with food, shelter, and medical care in purpose-built villages near the construction sites. The discovery of the workers' village at Giza, with its bakeries, infirmaries, and even evidence of fish imported from the Nile Delta, reveals that these laborers were valued assets, not disposable tools. Their well-being was directly tied to the project's success. This same principle of communal effort appears on Easter Island. There, evidence suggests that Moi production was a clan-based endeavor. Different family groups would have pooled their resources and labor to carve and erect their own ancestral figures, a process that strengthened social bonds and demonstrated a clan status and piety. The motivation was a powerful mix of religious fervor, civic pride, and social obligation. The very act of building together forged a shared identity, turning a disparate group of individuals into a unified force capable of moving mountains. This intricate organization was the invisible architecture that supported the visible stone, and it was all guided by a hidden language of numbers and ratios, a mathematical precision etched into the very proportions of the giants they raised. The true genius of these builders was not just in their brawn, but in their brains, in a silent, unseen language of numbers and geometry that gave their giants both form and stability. Long before the formalization of mathematics as we know it, ancient engineers wielded principles of geometry with an intuitive mastery. To create a statue that would not topple, they had to understand its center of gravity and how its weight would be distributed. They likely used simple but powerful tools like a plumb bob, a weighted string that always points directly to the Earth's center, to ensure every vertical line was true. A single degree of tilt in a multi-ton statue could create catastrophic stresses over time, so this precise alignment was non-negotiable. For their horizontal measurements, they turned to standardized units. In Egypt, the cubit was the rule of measure, a length based on the distance from a man's elbow to the tip of his middle finger, typically around 20 inches. Every dimension of a temple or a statue was a multiple of this unit, a system that allowed for perfect scaling from a small clay model to a full-sized colossus. Imagine an overseer with a knotted cord, pacing out the foundation and calling out measurements in cubits, his voice translating abstract numbers into the physical reality of a future giant. This mathematical precision extended to aesthetics as well. Greek sculptors are often credited with employing the golden ratio, a specific proportional relationship found throughout nature, to create a sense of perfect, harmonious beauty in their statues of gods and heroes. While debated, the presence of such ratios suggests a conscious effort to encode a universal ideal of perfection into their stonework. The principles were not locked away in textbooks. They were lived knowledge, passed from master to apprentice on the dusty floors of workshops, where scaled drawings were sometimes etched directly onto prepared walls or flat stones. These full-sized blueprints guided the carvers, ensuring that the curve of an eyebrow or the width of a shoulder was exactly as the master sculptor intended. This fusion of science and spirituality is perhaps most beautifully evident in the celestial alignments of some monuments. Certain colossi were positioned with such care that on specific days of the year, the rising or setting sun would illuminate their faces, or they would cast a shadow in a ritually significant direction. This was not a coincidence. It was a deliberate act of engineering that connected the earthly realm with the cosmos, a stone prayer aligned with the heavens. The intellectual rigor behind this apparent brute force reveals a civilization that saw no separation between the practical and the sacred, where every measurement was a step toward a divine order. This profound motivation, this deep-seated need to connect with something greater, was the very soul that animated the stone. A giant of stone was never just a monument, it was a vessel. These immense figures pulsed with a life far beyond their mineral composition, serving as direct conduits to the divine for the communities that built them. For the Rapa Nui people, each Moai was far more than a carved likeness. When its white coral eyes were finally set in place, the statue was believed to be activated, infused with a sacred spiritual energy they called mana. This power, channeled from deified ancestors, was thought to flow from the statue and blanket the island, ensuring fertile land, plentiful fishing, and the continued survival of the people. The Moi were not passive observers. They were active participants in the community's spiritual health, their silent gaze a constant reminder of a covenant between the living and the ancestral world. This relationship was cemented through ritual. At the Ahu platforms, ceremonies were held where offerings of food and precious goods were laid before the statues, a tangible exchange meant to honor the ancestors and maintain the flow of their protective mana. In Egypt, the concept was strikingly similar, though framed through the lens of a god-king. A colossal statue of a pharaoh was not a mere representation of the ruler. It was a physical body for his divine ka, or soul spirit. The statue was a place where the god could manifest on earth. Priests would perform daily rituals, offering it food, drink, and incense, dressing it in linens, and reciting prayers to sustain the divine presence that, in turn, sustained the entire kingdom. This spiritual function was inextricably linked to raw political power. A pharaoh who could commission such a giant was demonstrating his unique connection to the gods, legitimizing his right to rule through this overwhelming display of piety and resources. The Greek Colossus of Rhodes offers another powerful example. This towering bronze figure was not a king, but a depiction of the sun god Helios, the city's patron deity. Its construction was an act of immense thanksgiving, funded by the sale of siege equipment left behind by a defeated enemy. By raising this titan over their harbor, the people of Rhodes were not just building a wonder of the world. They were making a perpetual offering to the god they believed saved them, a permanent prayer for continued protection that also served as a stunning advertisement of their city's wealth and devotion to any ship that sailed into their waters. This profound spiritual dimension explains the staggering investment of time, labor, and treasure. These societies were not merely building statues, they were building relationships with the cosmos, prioritizing the spiritual well-being of their community over what we might view as more practical concerns. The very ground they stood on, the wind that weathered them, and the resources available, all played a decisive role in how these spiritual ambitions were given physical form. The very landscape became a demanding partner in this ancient dance of creation. These civilizations did not conquer their environments, they learned to collaborate with them, turning deserts, rivers, and remote shores into active participants in their monumental work. The dry, arid air of Egypt, for instance, while harsh on the laborers, acted as a natural preservative. It safeguarded the wooden sledges, the papyrus ropes, and even the administrative papyri that detailed the logistics, granting us a clearer window into their methods. Contrast this with the challenges of Easter Island, a tiny, isolated speck of land in a vast ocean. With no outside resources to call upon, the Rapa Nui had to be entirely self-sufficient. Every tool, every rope, every ounce of sustenance for the workers had to come from the island itself, a reality that shaped the scale and pace of their Moai production in profound ways. Ancient engineers possessed a remarkable talent for seeing opportunity in the terrain. They did not fight the Nile's annual flood, they harnessed it. They planned their transport of heavy stones for when the river was high, using its buoyant power to move loads that would have been immovable on land. They strategically positioned their temples and colossi against solid rock formations, using the natural bedrock as a stable backstop or foundation that would resist shifting over centuries. Even the seasons dictated the rhythm of work. In Egypt, the inundation of the Nile, which flooded the fields from July to November, was also a period when farmers were freed from agricultural labor. This seasonal downtime created a massive, available workforce that could be conscripted for state projects. a perfect synchronization of the agricultural and monumental calendars. This deep connection to the environment extended to a foresight about preservation. The ancient builders knew their creations were in a constant battle with the elements. Wind-driven sand could act like a natural sandblaster, slowly erasing fine details from a statue's face. They accounted for this by selecting harder stones for exposed features or by orienting monuments to minimize the prevailing wind's impact. A stunning modern echo of this ancient concern is the story of the Abu Simbel temples in Egypt. In the 1960s, the entire complex was meticulously cut apart and moved to higher ground to save it from the rising waters of Lake Nasser created by the Aswan High Dam. This colossal 20th century project was driven by the same fundamental impulse that guided the original builders, a desire to protect a cultural treasure from an environmental threat. It proves that the conversation between human creation and the natural world is timeless. This intimate relationship with the earth forced a constant, pressing need for invention, pushing the boundaries of what was thought possible with the materials at hand. Every innovation was born from the sheer necessity of moving the immovable. Ancient engineers were relentless problem solvers, viewing each failure not as a defeat, but as a lesson carved in stone. Their greatest breakthroughs often came from borrowing and adapting ideas from other crafts. The same principles of leverage and buoyancy that allowed a massive wooden ship to carry tons of cargo were applied to moving stone giants. A shipwright's understanding of how to distribute weight evenly across a hull directly informed the design of the massive barges that floated obelisks down the Nile. This cross-pollination of knowledge was the lifeblood of progress. In Egypt, the simple ramp evolved into a sophisticated tool. Engineers began constructing spiraling ramps of mud brick and rubble that coiled around the rising structure of a pyramid, allowing workers to drag blocks higher and higher. This was not a sudden revelation, but a gradual refinement over generations, each project adding a new layer of efficiency. Perhaps the most significant leap was the incorporation of the pulley. While the earliest pulleys were simple wooden wheels with a groove for a rope, their introduction transformed lifting operations. A single fixed pulley might not reduce the force needed, but it changed the direction of that force, allowing a team to pull downward with their full body weight, a far more effective and secure position than trying to haul a rope upward. Later, the development of compound pulley systems with multiple wheels dramatically multiplied the lifting power of a single team, allowing them to hoist heavier stones with greater control. This spirit of adaptation knew no borders. The Polynesian method of making the Moi Walk was itself a stunning energy-saving innovation. By rocking the statue from side to side, a smaller team could achieve what would otherwise require a massive, coordinated drag over rough terrain. It was a brilliant, localized solution to a universal problem. These advancements were not guarded secrets. Along bustling trade routes from the Mediterranean to the South Pacific, knowledge flowed. A technique for securing a rope learned by a sailor in a distant port might find its way to a quarry months later, shared between craftsmen who understood the universal language of physics and strain. This collaborative trial-and-error process also led to the development of composite tools. A stone hammer might be fitted with a more shock-absorbent wooden handle, or a copper chisel would be cast with a specific angle for better chip removal. In some cultures, this innovative spirit extended to the use of animal power. While there is little evidence of animals moving the stones themselves, oxen or donkeys might have been used to transport the vast quantities of food, water, and tool-making materials needed to sustain the human workforce, freeing up more hands for the precise, skilled labor. One of the most debated theories among archaeologists involves the hypothetical use of water management on a grand scale. the idea suggests that builders might have dug temporary canals right up to a statue's base, floating it into position on a controlled tide of water and mud. Though evidence is scant, the theory highlights the incredible creativity we are willing to attribute to these ancient minds, because their proven accomplishments already border on the miraculous. Yet for every ingenious success, there were countless moments of heart-stopping risk and catastrophic failure. The shadow of failure loomed over every stage of this monumental work. A single frayed rope, a misplaced lever, or an unexpected rainstorm could turn years of labor into a pile of shattered rock in an instant. The risks were not hypothetical. They were a constant, grinding reality. The Unfinished Obelisk in Aswan is the most famous testament to this peril, a giant eternally trapped in its granite bed by a catastrophic crack. But for every such famous failure, there were countless smaller, unrecorded disasters. A Moai, halfway through its walking journey across Easter Island, could have tipped too far and shattered on the volcanic rock, its spiritual mana lost forever along with the immense investment of its clan. The human cost was equally staggering. Egyptian medical papyri described treatments for crushed limbs and spinal injuries, grim evidence of the dangers faced by workers maneuvering multi-ton stones. The psychological toll on these laborers, toiling for years under the ever-present threat of maiming or death, is almost impossible to measure. They worked knowing that a single moment of miscommunication could be their last. Beyond the immediate physical dangers, these projects constantly battled the specter of resource exhaustion. A prolonged drought could decimate the food supply for a worker village. A shortage of quality timber for levers and sledges could bring the entire operation to a halt. On Easter Island, this precarious balance ultimately tipped. The very act of Moai construction, which required massive quantities of wood for transport and rope, is thought to have contributed to the deforestation of the island. This environmental collapse, intertwined with societal pressures, serves as a sobering cautionary tale of how the drive to build giants could ultimately undermine the civilization that created them. The economic strain was immense. A pharaoh's treasury could be drained by a single, failed obelisk erection, forcing a redesign of entire temple complexes or a scaling back of royal ambitions. This was high-stakes engineering with no safety nets. Every successful colossus that stands today is not just a monument to ingenuity, but a memorial to the risks overcome, the near disasters averted, and the perseverance that refused to yield to the sheer weight of the challenge. How can we possibly understand the reality of these ancient feats without witnessing them ourselves? The shadow of failure is a powerful teacher, but how can we truly measure the ingenuity it forced from ancient minds? This question drives modern experimental archaeology, a field where theory meets the unyielding reality of stone and rope. Researchers and dedicated volunteers are now stepping back in time, not with books, but with their own hands, using painstakingly recreated tools to carve and move multi-ton blocks under conditions meant to mirror the ancient world. This is not academic speculation, it is a tangible, physical dialogue with the past. The goal is simple yet profound, to test the feasibility of historical methods by actually trying them, often with startling results that rewrite our assumptions about the labor and intelligence required. The journey of a Moai, for instance, was long thought to be a simple drag across the island on log rollers. But when a team from a major documentary series put a full-scale replica on ropes and tried the oral tradition of making it walk, the results were revolutionary. With coordinated teams rocking the statue from side to side, the giant stone figure truly did appear to shuffle forward, a method that required far fewer people than a straight pull and aligned perfectly with the worn roads found on the island. It was a eureka, a moment born not from a dusty text but from sweat and strain. Expert analysis from these experiments consistently points to one overwhelming conclusion. Ancient builders possessed a profound, intuitive grasp of physics that we are only now beginning to fully appreciate. They understood leverage, balance, and friction not as abstract formulas, but as living forces to be manipulated with wood and cordage. To further decode this knowledge, researchers now employ sophisticated three-dimensional modeling to simulate these ancient processes. A computer can run 1,000 digital trials of an obelisk being raised, calculating stresses and identifying failure points long before a single real-world volunteer lifts a lever. This virtual testing ground is then validated by the raw, physical work of interdisciplinary teams. Archaeologists, engineers, master carvers, and even professional riggers come together, each lending their specialized perspective to the puzzle. A modern rope expert, for example, can look at the wear patterns on an ancient stone sledge and immediately understand how the ropes were likely secured and the direction of pull, insights that a pure historian might miss. One of the most revealing case studies involved the replication of an Egyptian obelisk raise. Using the sandpit method described in ancient texts, a team successfully erected a substantial stone monolith. The most surprising finding was not that it worked, but how efficiently it worked. The number of people required was significantly lower than previous scholarly estimates had suggested. This reshapes our entire perception of the labor force, hinting that these projects relied more on brilliant technique than on limitless human resources. This hands-on approach does more than just test theories. It builds a visceral bridge across the centuries. When a volunteer feels the immense, living weight of a stone block shift on a lever, or hears the specific groan of a rope under ultimate tension, they are sharing a direct physical experience with an ancient worker. They are learning the same lessons, feeling the same fears, and ultimately, understanding the same triumphant joy when the impossible is finally achieved. This shared struggle across time offers a new, deeply human perspective on our past. It reveals that the greatest resource was not just muscle, but a collective, accumulated wisdom passed from one generation of builders to the next. This universal drive to create the monumental connects cultures separated by vast oceans and time, inviting a direct comparison of their methods and their meaning. A world map of these stone giants reveals a stunning diversity of form and function. The stoic Moai of Easter Island stand in stark contrast to the serene, seated Buddha of Leshan in China, and both differ from the legendary, long-lost Colossus of Rhodes. Yet, despite their unique cultural skins, they share a common skeletal structure of engineering principles. The most fundamental shared challenge was stability. Whether it is the Great Sphinx of Giza, with its massive lion body providing a low, wide base, or the Leshan giant Buddha, carved in a stable seated posture directly into a riverside cliff, every engineer was solving the same equation: how to keep a massive weight from toppling. This universal need to conquer gravity led to remarkably similar solutions across the globe, primarily through a profound understanding of a low center of gravity and wide foundations. Yet the environment dictated the methods. On Easter Island, with its soft volcanic tuff, the Moai were free-standing monoliths. In Asia, where massive sandstone cliffs were abundant, the most efficient solution was to carve the statue in situ, turning the mountain itself into the monument and eliminating the Herculean task of transport altogether. This choice of living rock versus quarried block is the single greatest differentiator in their construction. The Colossus of Rhodes represents a third, audacious path. It was not carved from stone but cast in bronze, an assembled giant of many pieces. Where a Moai is a single, multi-ton piece of rock, the Colossus was a feat of metalworking and structural engineering, a hollow shell built around a stone and iron framework to withstand the winds of its harborside home. These approaches also created vastly different artistic signatures. The Moai are abstract and angular, their features stark and powerful. The Buddhist colossi are often fluid and naturalistic, depicting folds of robes and calm, meditative expressions. These styles were not merely aesthetic choices, they were born from the stone itself and the tools available. The construction timelines tell their own stories. A Moai might take a clan a year to carve and move. The Leshan giant Buddha was a communal project so vast it took nearly a century to complete, its creation spanning generations. This highlights another key variable: societal organization. The Moai were often clan-based projects, while the Great Buddha or the Great Sphinx required the centralized power of a state or a deeply unified religious community to marshal such sustained effort. Their preservation states today offer a final, poignant point of comparison. The solid, cliff-carved Leshan Buddha endures, weathered but intact. The assembled Colossus of Rhodes fell in an earthquake after just a few decades, its pieces eventually sold for scrap. The Moai, once toppled by internal conflict and environmental change, are now being resurrected by modern hands. This global perspective shows us that while the human impulse to build giants is universal, the expression of that ambition is beautifully, ingeniously local. But for every stone giant that stands in the light of history, another exists in the shadowy realm of story and speculation. These legends are not mere fanciful stories, they are the cultural memory of the stones themselves, passed down through generations. When oral tradition on Easter Island insists the Moi walk to their platforms, it is not a child's fantasy. It is a poetic, powerful encapsulation of the actual rocking method modern experiments have proven viable, a truth preserved in the language of myth. Similarly, the enduring image of the Colossus of Rhodes straddling the harbor mouth is a magnificent exaggeration, a symbol of the city's defiance and dominance burned so deeply into the historical record that it became visual fact. These narratives served a crucial purpose. They transformed a staggering engineering achievement into a divine or heroic act, elevating the work of human hands into the realm of the supernatural. This answered a deep cultural need, explaining the otherwise inexplicable and binding the community together with a shared, awe-inspiring origin story for the giants in their midst. Greek historians like Pliny the Elder did not just record the Colossus's dimensions, they wove it into a narrative of resilience, a monument forged from the melted-down weapons of a defeated enemy. The statue was not just a wonder, it was a permanent trophy, a story of victory carved in bronze for all approaching ships to see. This blurring of history and folklore continues powerfully in our modern media. Blockbuster films and epic video games consistently depict ancient wonders not as they were, but as our myths imagine them, complete with magical powers or impossible scale. This pop culture reinforcement ensures that the legendary Colossus, shining and godlike, often overshadows the historical one in our collective imagination. Yet, within these exaggerations, archaeologists often find precious kernels of truth. An outlandish legend about giants building a wall might encode a forgotten memory of a tall, culturally different people who introduced new stoneworking techniques. The myth becomes a puzzle box, and the key is understanding the human psychology that created it. The desire to attribute such works to gods or giants reveals a profound humility, or perhaps an immense pride, in the face of a legacy so grand it seems to surpass human capability. This narrative layer, woven from both fact and fantasy, is the soul of the Colossus, the story that gives the stone its voice. That voice would echo through the ages, challenging and inspiring every engineer who dared to dream in a grand scale. The echoes of these ancient building sites did not fade with the empires that created them. They resonated through the centuries, becoming a quiet blueprint for the monumental works of later eras. When Renaissance artists gazed upon the ruins of Rome, they were not just admiring statues. They were absorbing the principles of scale, proportion, and ambition that would fuel their own masterpieces. The same engineering logic that guided a multi-ton Moai across Easter Island found new life in the construction of Roman aqueducts and the soaring vaults of Gothic cathedrals. Master builders, raising immense blocks of stone hundreds of feet into the air, relied on the same fundamental tools: the lever, the pulley, and the inclined plane. The treadwheel crane, a medieval innovation powered by men walking inside a giant wheel, was a direct descendant of ancient lifting technology. It operated on the same principles of mechanical advantage that allowed a small team to steer a granite colossus into its final position. These machines were the industrial revolution of their day, and their DNA can be traced back to the quarries of Egypt and the hillsides of Rapa Nui. The organizational genius behind these projects may be their most enduring gift. The complex labor divisions, the specialized roles, and the logistical planning required to feed and house a massive workforce became a model for every large-scale project that followed. This ancient template for managing human resources on a colossal scale laid the administrative groundwork for everything from the canal systems of the 18th century to the sprawling public works of the industrial age. We see this legacy most vividly in the European obsession with Egyptian obelisks. During the Renaissance and Baroque periods, popes and monarchs embarked on their own epic quests to acquire, transport, and re-erect these ancient monoliths as symbols of their own power and learning. The moving of the Vatican obelisk in 1586 was a spectacle of engineering that rivaled the original constructions, requiring hundreds of men, miles of rope, and a fleet of ships, all guided by a renewed study of ancient texts and methods. This was not mere imitation. It was a dialogue with the past, proving that the solutions devised by ancient engineers were not lost secrets, but reproducible formulas for moving the immovable. Today, these principles are not forgotten relics. They form a critical chapter in modern engineering and archaeology curricula, where students analyze the construction of the Great Pyramid to understand static load distribution, or study Moai transport to grasp the physics of friction and center of gravity. The challenges faced by those ancient builders and the ingenious ways they overcame them continue to inform how we approach our own monumental tasks, from building skyscrapers to planning space missions. The true legacy of the Colossi is this unbroken chain of inspiration, a testament to human ingenuity that stretches across millennia. Yet, for all their earthly grandeur, these stone giants were often built with their eyes turned toward the heavens. These stone giants were not just earthly monuments, they were celestial calendars carved in rock. The precise orientation of a colossus was often as important as its divine features, engineered to capture a specific beam of sunlight or cast a meaningful shadow on a sacred day. This was a deliberate fusion of architecture and astronomy, a way to ground cosmic cycles in the physical world. In Egypt, many colossal statues of pharaohs were positioned to face directly east, their stone eyes awaiting the dawn. As the sun, the god Ra, broke over the horizon on the morning of the equinox, its rays would strike the statue's face first, symbolically filling the ruler's form with the divine essence of creation itself. This was more than a beautiful spectacle. It was a public demonstration of the pharaoh's intimate connection to the gods, a yearly renewal of his mandate to rule that was visible to all. The knowledge required for such precision was profound. Priests and surveyors used simple but effective tools like the merkit, a forked sighting stick that functioned as a primitive transit to track the movements of stars and plot perfect alignments on the ground. They understood that the sun did not rise in the same spot every day, and they meticulously charted its slow migration north and south along the horizon throughout the year. This celestial choreography was then locked into the foundation stones of their temples and statues. Far across the Pacific, the Moai of Easter Island also participated in this cosmic dialogue. While many gaze inland over their villages, some are positioned on coastal platforms, or ahu, that are aligned with the rising sun during the solstices. Others are thought to face specific points on the horizon that were significant to the clan's ancestral origins, connecting the living community not just to their deified ancestors in the statues, but to their mythical homeland across the sea. The interplay of light and stone also served a practical purpose. The shadows cast by these giants could function as massive public timekeeping devices. A visitor to an Egyptian temple complex might note how the shadow of a colossal obelisk would touch a specific mark on the pavement at noon, signaling the height of the day, or how it would point toward a particular shrine as the seasons changed. This integration of time, faith, and stone is perhaps nowhere more spectacular than at the great temple of Abu Simbel. Here, the architects performed a masterstroke of solar engineering. The temple was carved deep into a cliff face, with 4 seated colossi of Ramses II guarding its entrance. They designed it so that twice a year, around the king's birthday and his coronation day, the rising sun would penetrate the dark, 200-foot-long hallway. The beam of light would travel inward, bypassing other statues in the hall, to illuminate the innermost sanctuary, where the figures of Ramses and the gods Ptah, Amun-Ra, and Ra-Horakhti were seated. For a few magnificent minutes, the gods and the pharaoh were bathed in radiant light, an event that still draws crowds of modern spectators. The sole exception was the statue of Ptah, the god of darkness, who remained appropriately in shadow. This celestial dimension reveals a layer of sophistication we are only beginning to fully appreciate. It shows that the builders saw their world as an interconnected whole, where the movements of the heavens directly influenced life on earth, and where a king's power was reaffirmed by the sun itself. This deep spiritual drive, however, required a staggering investment of real-world resources. The sheer economic weight of a stone giant could reshape an entire society. To feed, clothe, and equip an army of workers for years required a staggering diversion of resources. A national budget poured directly into the earth. State treasuries and temple coffers funded these epic projects, creating a monumental economy within the greater one. In Egypt, this system ran on bread and beer. Papyrus records from Deir el-Medina, the village for the royal tomb workers, detail precise daily rations, with laborers receiving loaves of bread, jugs of beer, and portions of fish and vegetables. The grain to pay these wages was drawn directly from the pharaoh's vast storehouses, effectively turning agricultural surplus into stone. This was not merely a salary. It was a sophisticated mechanism for redistributing wealth and fueling a massive, state-sponsored employment program. For the duration of the project, a whole sector of the population was lifted from subsistence farming into skilled, compensated trades. A young man might enter the workforce as a quarry laborer and, over a decade, learn the art of stone dressing or lever mechanics, his newfound expertise becoming a valuable asset to his community. This economic engine, however, ran on a precarious balance. The constant demand for copper for chisels, for timber for sledges and levers, and for abrasives for polishing stimulated regional trade networks. Quarries became hubs of commerce, with merchants arriving from distant lands to barter for rare, high-quality stones or to sell essential supplies. the Colossus of Rhodes stands as a powerful testament to this economic duality. Historical accounts suggest it was funded by selling the abandoned siege equipment of a defeated enemy, transforming the tools of war into a symbol of peace and prosperity. Its immense bronze skin required a fortune in metal, fueling mining and smelting industries, while its fame as a wonder of the world undoubtedly drew merchants and travelers to its harbor, boosting the city's commercial life for generations. Yet the shadow of this prosperity was the risk of exhaustion. On Easter Island, the very act of Moai construction is thought to have accelerated an ecological and economic collapse. The insatiable need for tall, straight trees for transport logs and strong fibers for ropes appears to have contributed to the island's deforestation. As the forests vanished, so did the means to build fishing canoes and sustain the soil, creating a vicious cycle where the drive to honor the ancestors may have ultimately undermined the society's ability to feed itself. This reveals the ultimate trade-off, a civilization betting its present resources on a legacy for the future, a gamble that could forge a timeless wonder or sow the seeds of its own decline. Today, the economic legacy of these giants has transformed. The same colossi that once drained treasuries now generate immense value as the centerpieces of a global tourism industry, their preservation a complex and costly endeavor in its own right. The legacy of these stone giants now faces a new era of threats, from the slow creep of pollution to the relentless forces of climate change. Preserving them is a race against time, a global effort that blends ancient wisdom with cutting-edge science. Teams of archaeologists and conservators work like modern-day physicians, diagnosing ailments in the stone and applying delicate treatments to extend their lifespan. They use chemical consolidants, carefully injected into porous rock, to bind crumbling surfaces from within, and install nearly invisible structural supports to stabilize a leaning monolith. Perhaps the most crucial tool is digital documentation. Through high-resolution laser scanning and photogrammetry, they create perfect three-dimensional models of every statue. These digital twins are more than just records, they are insurance policies. Should a fragment fall or damage occur, conservators have a precise blueprint for repair, a virtual copy that will outlast the physical stone itself. This work is often a collaborative international endeavor, with organizations like UNESCO providing crucial funding and expertise to protect these wonders as a shared human heritage. On Easter Island, the restoration of the Moai is a continuous process. Teams have carefully re-erected toppled statues, securing them on their ahu platforms with modern materials designed to withstand earthquakes, all while respecting the sacred nature of the sites. In Egypt, the challenge is managing the impact of millions of visitors. Solutions include building viewing platforms that control foot traffic, installing climate-controlled enclosures around the most fragile statues, and strictly limiting the number of daily tickets to reduce humidity and carbon dioxide levels from human breath. This creates a constant ethical tightrope, balancing the public's right to access these cultural treasures with the absolute necessity of protecting them from the wear and tear of that very access. Funding is a perpetual struggle. Conservation is expensive, requiring specialized materials and highly trained experts, and the money must often be fought for in competitive grants or drawn from limited government budgets. This leads to difficult choices about which sites are saved first. The ethical questions run even deeper. How much of a statue should be restored? Is it right to replace a missing arm using modern materials? Or does that erode the authenticity of the ancient artifact? These debates are not new. A fascinating case study is the Colossi of Memnon in Egypt. After an earthquake damaged the northern statue in 27 BCE, the Romans under Emperor Septimius Severus performed a massive restoration, carefully reassembling the broken pieces. This ancient repair, still visible today, informs modern conservators. It shows a centuries-old recognition that these monuments were worth saving, and it provides a long-term record of how different stones and mortals behave over millennia. The commitment to conservation is a profound act of respect. It honors the labor and vision of the original creators, ensuring that their stone declarations are not lost to the winds of time. These preserved giants carry more than just the weight of stone. They are heavy with meaning, their silent forms speaking a complex language of power, faith, and identity. Every curve and contour of these giants was a deliberate word in a silent language of stone. The stoic faces of the Moi were not blank. They were carved with a specific brow line and jaw to convey ancestral authority, their gaze an eternal watch over the clan. These details went far beyond artistry. They were a direct communication system for cultures often without widespread literacy. A crown on an Egyptian pharaoh's colossus was not just a royal hat, it was a complex symbol of his right to rule, woven with motifs of the cobra and the vulture to declare his power over both Upper and Lower Egypt. In the same way, crossed arms on a statue were not merely a relaxed pose, they were a near-universal sign of protection or of a sacred, unbreachable boundary, a gesture that said this figure guards what lies beyond. The most profound example of this symbolic activation comes from Easter Island. A completed Moi was not considered alive until its eyes were set in place. During a special ceremony, artisans would fit the sockets with white coral eyes and pupils of obsidian. This was the moment of awakening, when the statue was believed to be filled with mana, the spiritual energy of the deified ancestor it represented. It transformed the rock from a monument into a vessel, a living conduit between the community and the divine. Expert analysis of these symbols reveals the rigid hierarchies of the societies that built them. The size and ornamentation of a colossus directly reflected the status of its subject, creating a visual pecking order in stone that everyone from peasant to priest could understand. Inscriptions carved into the base or the statue itself acted as permanent historical records, listing royal titles, military victories, or pious dedications to the gods. This symbolic language was never static. Over centuries, styles evolved. Early Greek Kouros figures were rigid and formal, but later Greek colossi embraced idealism. They depicted gods and heroes with perfected, harmonious proportions, their serene faces and powerful physiques representing a cultural aspiration toward human perfection as a reflection of the divine order. This was not a pursuit of realism, but of an elevated truth. The symbolic codes woven into these giants were meant to be read and felt by everyone who saw them, a permanent public broadcast of a civilization's deepest values and beliefs. This silent communication was so powerful that to stand in the shadow of a completed colossus was to undergo a profound psychological transformation. That silent language of stone spoke directly to the human heart. To stand in the shadow of a completed colossus was to undergo a profound psychological transformation. The sheer, overwhelming scale triggered an immediate sense of awe, a humbling recognition of one's own smallness in the face of a power that was both human and divine. This was not an accident, it was the entire point. For the average farmer or fisherman in ancient Egypt, approaching the towering statues of a pharaoh flanking a temple gate was an act of submission and devotion. The stone face, many times larger than life, was an undeniable declaration of the king's authority, a psychological anchor that reinforced the entire social order. You felt your place in the world simply by looking up. This experience was magnified during public ceremonies. Historical accounts and tomb paintings depict vast crowds gathering in plazas before these giants for festivals and royal announcements. In that shared space, surrounded by thousands of fellow citizens all gazing up at the same immense figure, individual identity temporarily melted away into a collective one. A shared feeling of pride, fear, or reverence would ripple through the crowd, forging a powerful sense of unity and common purpose. The Colossus became a focal point for communal identity, a symbol that everyone, from the highest priest to the lowest laborer, could look to and say, "This is who we are. This is what we can achieve together." The process of building them was just as important as the finished product. The very act of shared labor, of thousands of people working toward a single, magnificent goal, created social bonds that lasted for generations. There was a collective pride in the accomplishment, a story to tell their children and grandchildren about the time they helped raise a giant from the earth. This shared struggle and eventual celebration turned a disparate population into a cohesive society. These stone giants also served as the primary textbooks for their cultures. In an age before widespread literacy, the statues themselves were the lesson. The symbols carved into a pharaoh's headdress, the specific posture of a Moi, the attributes held by a Greek god, all passed down complex stories, religious beliefs, and historical events. A parent could point to a colossus and explain the story of a great king or a powerful ancestor, ensuring that the community's values and history were visually encoded for everyone to see and understand. This educational role extended to the skilled trades. The knowledge of how to carve, move, and raise these monuments was a living curriculum, passed from master to apprentice on the job. A young stoneworker learned geometry by snapping guidelines, physics by feeling the balance of a lever, and artistry by studying the master's chisel strokes. The Colossus was both the exam and the diploma. Travelers' journals from later centuries capture the enduring emotional weight of these sites. Even in ruins, a toppled colossus possessed a haunting power. Writers often described a mix of melancholy and inspiration when confronting these fallen giants, a sense of connection to a lost world and its people. This human response, felt across millennia, reminds us that art on such a scale is never just decoration. It is an active force that can shape a society's mind, reinforce its structure, and echo its values long after the civilization itself has faded. Yet for all we have pieced together, the silent stones still guard profound mysteries. Even after centuries of study, these silent giants refuse to surrender all their secrets. The field of archaeology is alive with fierce debates over the very details we thought we understood. Take the Colossus of Rhodes, that legendary bronze titan. While we know it was cast in sections, the precise mechanics of its assembly remain a heated mystery. How did workers hoist and connect the massive bronze plates, some weighing many tons, to a stone and iron framework over 100 feet in the air? Was it a system of massive earth ramps or an ingenious use of floating cranes in the harbor? The lack of physical evidence means every new theory is a plausible guess, a best-fit model for a puzzle missing most of its pieces. This uncertainty inevitably opens the door for more sensational explanations, like ancient alien interventions, a notion most serious scholars dismiss entirely. They argue this idea robs our ancestors of their hard-won ingenuity, suggesting that the only way humans could have achieved such feats was with otherworldly help. The reality is far more compelling, a testament to human creativity and relentless problem-solving. Nowhere is this debate more active than on the rocky slopes of Easter Island. Here, the landscape is littered with clues and contradictions. Nearly half of the Moi were abandoned en route, still lying in the island's ancient roads. Were these casualties of clan warfare, resource collapse, or a simple transport miscalculation that shattered a generation's work? The evidence on the ground fuels a central controversy. Did the Moi glide on log rollers, or did they truly walk? Experimental archaeology has shown the walking method is viable, yet some researchers point to the wear patterns on the roads and the sheer number of abandoned statues as evidence for a simpler, drag-based system using wooden sledges. Each new experiment provides data, but the definitive answer remains just out of reach, hidden in the eroded paths of the past. These debates are further complicated by the tools we use to date the monuments. Controversies over radiocarbon dating from associated organic material can shift a statue's age by centuries, dramatically altering the historical context of its creation. And how do we weigh the value of oral histories passed down through generations against the hard, but often scarce, physical evidence? An elder's story about the Moi walking was long considered folklore until modern tests gave it serious scientific credence. This dynamic interplay between emerging data and long-held theories is what keeps the study of these colossi so vibrant. Every new discovery, whether a laser scan of a hidden quarry or a fresh analysis of tool marks, has the potential to overturn decades of accepted wisdom. These unanswered questions are not failures of science. They are the very engine of discovery, reminding us that the past is not a closed book but a living conversation. The enduring legacy of these stone giants is not just in their physical presence, but in their perpetual challenge to our understanding, inviting each new generation to look closer and ask the next great question. These stone giants stand as a permanent dialogue between human ambition and the physical world. They are not cold, silent relics, but vibrant testaments to what we can achieve when we work together toward a breathtaking goal. Our journey has taken us from the dust of the quarries to the final, heart-stopping moment of raising a giant into the sky. We have seen how simple tools, when guided by profound intuition, could coax a mountain from its bed, shape it with patient hands, and convince it to stand for millennia. The true material was not just granite or tuff, but ingenuity, faith, and an unbreakable collective will. The mathematical precision etched into their proportions, the celestial alignments locked into their foundations, and the rich symbolism carved into their features all tell a deeper story. This was innovation forged in the fires of necessity, driven by a belief in something greater than oneself. The next time you encounter a historical mystery, a feat that seems to defy logic, remember the Colossi. Look past the sheer scale and see the human hands, the coordinated effort, the brilliant failures, and the ultimate triumphs. Their legacy is a powerful lesson for our own modern challenges, reminding us that the most complex problems often yield to persistent collaboration and a bold vision. If this exploration into our shared past has sparked your curiosity, we would love to hear your thoughts in the comments. For more deep dives into the wonders of human history, be sure to subscribe. The giants of stone silently urge us to remember that with enough determination and unity, even our grandest dreams can, quite literally, be set in stone.